Hello friends, in this lecture we continue our discussion on chronic penny model using a Dirac comp and derive the allowed energy values in a 1D lattice. A Dirac comp is Dirac delta potentials arranged in a 1D lattice. We have derived the governing equation in the previous lecture. In the left hand side of the governing equation we have cos small k times a, and in the right hand side of the governing equation we have a function of capital Ka. Let me call this as f of capital K A. Note that capital K is related to the energy and small k is the wave vector of the block function. Allowed value of k is given by the periodic boundary condition. Using the governing equation, we are going to find the energy eigenvalues of block electrons in 1D lattice, where the potential is given by the Dirac comp. Next, we take the right hand side of the governing equation and plot f of Ka as a function of Ka. Using a Python code, let us plot the right hand side of the governing equation. Note that beta is the measure of the strength of the potential. Higher the value of beta, stronger is the potential. We are going to plot f of Ka for different values of beta. The function to be plotted is defined here in the code. This is the code for plotting the right hand side of the governing equation defined in this line. The value of capital K times A is varied from 0 to 4 pi. First we run the code for beta is equals to 2. Now let us run the code for another value of beta and let's take beta is equals to 4. This is the plot of f of Ka for beta equal to 2 and this is the plot for f of Ka for beta equal to 4. In the left hand side of the governing equation we have cos Ka. Note that f of Ka values shown by the red line in the plot has no restriction. For example, in case of beta equal to 2, the maximum value of f of Ka is around 3. In case of beta equal to 4, it is even higher. But cos Ka lies in a range of +1 and -1. Thus, the regions where f of Ka lies between -1 and +1 are the allowed regions. Allowed regions are shaded in blue in the figures. Remember that capital K is related to the energy and small k is wave vector of block function. Allowed regions are termed as energy bands and I have marked them as band 1, band 2, band 3, band 4, etc. in the ascending order according to their energy. Regions where f of Ka goes beyond +1 and -1 are forbidden regions and they are shaded in red in the figure. So these are the forbidden regions because f of Ka is either more than 1 or less than 1 in these regions. Forbidden regions are related to the band gap and their width increases with the increasing value of beta. For example, in case of beta is equals to 2, this is the width of one of the forbidden regions. And this is the width of the one of the forbidden regions for beta is equals to 4. Note that the width is much higher when beta is equals to 4. Thus, a stronger potential leads to wider band gap as expected. So, this is our governing equation which determines the allowed and forbidden regions. Capital K is related to energy. E is equals to h cross square capital K square by 2m. And multiplying and dividing by a square, we can rewrite E as h cross square by 2ma square times capital K a whole square. Thus, as capital Ka increases, the energy is increasing in this direction. If we plot energy along the vertical axis, then this is what we get. The allowed regions shaded in blue are termed as energy bands. They are shown in ascending order, that is, band 2 has higher energy than band 1, band 3 has higher energy than band 2, etc. Remember that small k are the wave vector of the block states given by the periodic boundary condition. If there are capital N number of lattice points in the 1D lattice, allowed values are Kn is equals to 2 pi small n divided by capital N. That is, there are capital N allowed values of K. This implies that there are N block states in each band. So that means band 1 has N states, band 2 has N states, band 3 has N states, and so on. And if we apply Pauli's exclusion principle, then we can put maximum 2n electrons in the first band, we can put maximum 2n electrons in second band, and so on. Width of each band generally varies from 1 to 10 eV. In a solid, capital N is 10 power 23. This implies that gap between energy levels within a band is very small, and this is of the order of 10 power minus 22 electron volt. Thus, energy values within a band are virtually continuous. Now, we are going to plot energy versus the wave vector small k. This is the governing equation, and we already have plotted f of Ka as a function of Ka. Regions where f of Ka goes beyond +1 and -1 are forbidden regions. For a given Ka, we calculate f of Ka here in the code and determine whether it is in the allowed or forbidden region in this line. If f of Ka is in the allowed region, we calculate the energy. We write the energy in this form and set this term equal to 1, such that energy is equals to Ka by pi whole square. In the code, we find energy in this step. For a given Ka, the wave vector of the block function is given by cos inverse f of Ka. If the energy lies in the first band, we calculate the energy, we calculate the wave vector, and we calculate the corresponding free electron energy here in the code. All the values are stored in different lists. Similarly, if the energy value lies in the second band, we calculate energy, we calculate the wave vector, and we calculate the corresponding free electron energy here in the code. Finally, we plot energy versus the wave vector and compare with the free electron energy. Note that free electron energy is obtained from the calculated value of the wave vector small k. This is the code to plot energy versus k. This is the governing equation to determine allowed or forbidden region. We determine the allowed or forbidden region using the if loop. Here we calculate the energy and wave vector of the first band. Here we calculate the energy and wave vector of the second band. Let us run the code for beta is equals to 2. Now let us calculate for some other value of beta. For example, beta is equals to 4. The dashed line denotes the energy of the free electrons. Solid red line shows the energy of the block electron in the first band, and solid blue line shows the energy of the electron in the second band. This is the plot of energy versus k for beta equal to 2, and this is the plot of energy versus k for beta equal to 4. From the plots, it is clear that the energy of the block and free electrons differ mainly in a region close to the Brillouin zone boundary. Away from the Brillouin zone boundary, free electron picture holds good. We also notice that energy gap increases with increasing strength of the potential. For example, for beta equal to 2, this is the energy gap, and for beta equal to 4, the energy gap is much larger than beta equal to 2. For mathematical convenience, we have used the Dirac-Comte type potential so far. However, actual chronic Penny model uses periodic potential barriers of finite width, not the Dirac delta type of potential. As shown here, the barriers have a width of b, and a is the lattice translation vector. Height of the barrier is u0. Consider the region between x equal to 0 and x equal to a. This region is located outside the barrier, that is u is equals to 0. In that case, the solution is a e power ikx plus b e power minus ikx, where k is equals to square root of 2me divided by h bar. Now consider the region between minus b and 0. This is a region located inside the barrier. In this case, the solution is c e power qx plus d e power minus qx, where q is equal to square root of 2m u0 minus epsilon divided by h bar. So far, this looks exactly like what we did for the tunneling problem. Now, because of the periodicity of the potential, we can apply Bloch theorem. For example, consider solution in the region between a and a plus b, that is this region. This has to be related to the solution between minus b and 0, that is this region. They are related because of the periodic potential, and they are related by this phase factor e power I k a plus b. Note that we can put the lattice points here, 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 and here. Thus, the lattice point located at minus b can be mapped to the lattice point located at plus a via a lattice translation vector of a plus b. That is why the Bloch function satisfies this equation. At x equal to a, psi of a is related to psi of minus b by this equation. And at x equal to a plus b, psi of a plus b is related to psi of 0 by this equation. In the region between x equal to 0 and x equal to a, the wave function is a e power ikx plus b power minus ikx. Thus, the first derivative of the wave function is ik a e power ikx minus b e power minus ikx. Now, in the region between minus b and 0, the solution is c e power qx plus d e power minus qx. And the first derivative is psi dashed is equals to q c e power qx minus d e power minus qx. Both psi and d psi dx is continuous at x equal to 0. Note that since we are dealing with a potential barrier of finite width, there is no discontinuity of the first derivative. Thus, putting x equal to 0 and equating the wave function, we get a plus b is equals to c plus d. Now, we put x equal to 0 and equate d psi dx. In that case, we get I k a minus b is equals to q times c minus d. Now, we match the wave function and its first derivative at x equal to a. In the region x lying between 0 and a, the wave function is a e power ikx plus b e power minus ikx. And its first derivative is ik a e power ikx minus b e power minus ikx. In the region x between minus b and 0, the wave function is c e power qx plus d e power minus qx. And its first derivative is q c e power qx minus d e power minus qx. Now, we already know that the wave function in this region lying between a and a plus b and lying between minus b and 0 are related via Bloch theorem and satisfy this equation. Applying Bloch theorem, the wave function and its first derivative at x equal to a and x equal to minus b are related by these two equations. Now, we have to equate the wave function at x equal to a. So, we put x equal to a in this equation and write the left hand side as a e power I k plus b e power minus I k a. And this part is equal to psi a given by this expression. Psi of minus b times the phase factor e power I k a plus b. From this equation, psi of minus b is c e power qb plus p e power q times b. And then we have the phase factor e power I k a plus b. Now we have to equate the first derivatives. So left hand side we just put x is equals to a in this equation such that we get ik a e power ik a minus p e to the power minus I k a. And in the right hand side, we put this term where psi dashed of minus b we can get from here. This is equal to q times c e power minus qb minus b e power qb times the phase factor e power I k a plus b. Now we have 4 equations and 4 unknowns a, b, c, and d. Solution exists if determinant of the coefficients of a, b, c, and d vanishes. If you apply this condition, then you get this equation. Note that in this equation, a is the lattice translation vector, b is the width of the potential, capital K is related to the energy, small q is related to the height of the potential as well as the energy, and small k is the wave vector of electrons. Equation 5, that is this equation, is qualitatively similar to the governing equation we derived for Dirac-Comp. Let us prove that. Let us take the limit b going to 0, that is width of the potential is vanishing and u naught tends to infinity, that is the height of the potential barrier becomes very high. In the limit u naught going to infinity, we see from this equation that q becomes much larger than capital K, such that we can write q square minus k square is almost equal to q square. Now, since b tends to 0, we have q times b is much less than equal to 1. And in this limit, sine hyperbolic qb is approximately equal to qb and cos hyperbolic qb is approximately equal to 1. Also, in the limit b tends to 0, a plus b can be approximated to be equal to a. Now we substitute all this in equation 5, that is this equation. So q square minus k square is approximately equal to q square, so we put it, and then we have divided by 2q k sine hyperbolic qb, this is approximately equal to q times b, then we have sine k plus cos hyperbolic qb is approximately equal to 1, and then we have cos of k, this is equal to cos of small k times a, because a plus b is approximately equal to a. And then we just rearrange the terms q square, b divided by 2 because 1q gets cancelled, and then we just multiply and divide by a times sine ka divided by k, and then we have plus cos ka, this is equal to cos of small k times A. And then we can rewrite this equation as beta, where beta is equals to Q square BA divided by 2. And then I have K times A. Beta is equals to Q square BA divided by 2. So now we have sine of K plus cos of K is equals to cos of small k times A. Note that this equation is exactly same as the equation we got for the Dirac-Comp. We have completed our discussion on how to solve time-independent Schrodinger equation in a periodic potential. This has been a long discussion, and let me summarize the most important steps. The first step is to write some generic form of the wave function in a periodic potential. This is given by the Bloch theorem. Let me quote Bloch himself. I found to my delight that the wave differed from the plane wave of free electrons only by a periodic modulation. Then we solved in two different routes. First one is a solution in reciprocal space. We do a Fourier series expansion of the potential and of the wave function. Using the Fourier components, we can express the time-independent Schrodinger equation in the form of a system of linear equations. Energy eigenvalues are obtained from the determinant of this matrix. In the second method, we solve the time-independent Schrodinger equation in real space using Kronig-Penney model. It is assumed that a potential barrier exists at every lattice point. We derive a governing equation by matching the wave function and its first derivative at every lattice point. Energy eigenvalues are obtained from the governing equation. Both the methods yield qualitatively similar results. For example, this is how the energy versus K diagram looks like when solved in reciprocal space, and this is how it looks like when solved in real space using Kronig-Penney model. When U or beta is very small, we call it a nearly free electron model of energy bands. The name originates from the fact that energy of the Bloch electrons is same as free electron energy except near the Brillouin zone boundary. For example, in this case, the energy of Bloch and free electrons differ mainly in this region, and in this case, the energy of the free electron and the Bloch electrons differ mainly in this region, which is close to the Brillouin zone boundary. Otherwise, the energy of the Bloch and free electron energies are identical. Note that I have used very high U and beta to exaggerate difference between Bloch and free electrons. You are advised to use smaller values to appreciate the name nearly free electron model of energy bands.